Okay, these are homework questions to keep going with Unit 4 homework. We left off at 69. 69 says, every 74 years, Halley's Comet is visible from Earth. Find the average distance of the comet from the sun in astronomical units. Okay, if you look on your formula sheet, we have two options. We could use this formula or this formula. This one's much harder, and we would need the mass of the sun. We'd be solving for the radius, the average distance that Halley's Comet is away from the sun. This is going to be a much easier way to do it, and the better way with the information that we're given. So let me go ahead and copy this formula down. All right, now we're just going to fill it out. So we have 3 of the 4 variables. Okay, we have the period for Halley's Comet. So we're going to say that A is the Earth, we'll say, and we'll say that B is Halley's Comet. All right, so that means that the period of A is the period of the Earth. We know that's 1 year. We know the period for Halley's Comet is 74 years. Now, the average distance that the Earth is away from the sun is 1 astronomical unit, so we use 1 there. And we're trying to find the average distance that Halley's Comet is away from the sun. So that's what we'll fill out. And all we have to do is solve for this average orbital distance that Halley's Comet is away from the sun. All right, to solve this, I would take the square root of both sides, which basically takes that 2 and puts it in the denominator here. Okay, if you learned that from Algebra 2. And then, actually, I'm sorry. Let me go the other way around. I'm trying to solve for this variable. So let me take the cube root of both sides. And that gets rid of this. And then I can solve for the, let me reciprocate both sides. So I'll have the average distance that Halley's Comet is away from the sun is equal to 1 over this distance, 1 over 74 to the 2/3. So I would do, I don't know, you can enter this whole thing in if you want, but I like to say inside the parentheses, so I would do 1 divided by 74, hit enter, and then raise that answer to the 2/3. And then do 1 divided by that answer. So I kind of work my way outside, and there's different ways to do it, but that gives you about 17.6. So basically the average distance that, that Halley's Comet is away from the sun is 17.6 astronomical units, which is actually 17.6 times the average distance that the Earth is away from the sun, which is 93 million miles. So you actually need to take 93 million miles, multiply by 17.6 to get the answer in miles. Okay, next question, 72, is an asteroid on Ceres has a mass of 7 times 10 to the 20 kilograms and a radius of 500 kilometers. And it wants to know what is G on the surface. Okay, so we're going to look at our formula sheet again and try to determine what formula to use. Okay, so here's our options. We've got the period, we've got the velocity. It might be helpful to write down what you have. You're given the mass and the radius, you're looking for G. So when you look at the formula sheet now, you can say, all right, so, oops, not that one. When you look at the formula sheet, you can say, I need, I have the mass, I have the radius, and I'm looking for G, small g, acceleration due to gravity. So I'm going to use this formula right here. Okay. All right, so all you have to do is plug it in and find G. So we have capital G, which is 6.67 times 10 to the negative 11, times the mass, which is 7 times 10 to the 20th, all divided by the radius squared. Now it's 500 kilometers, so I actually need to make that 500,000 meters squared, because we got to make sure we're in meters, so don't mess that part up. So you end up getting about 0.19, and that's meters per second squared. So you can compare that to, you know, on Earth it's 9.8 meters per second squared, a lot less. And it actually says, how much would a 90 kilogram astronaut weigh? Well, weight for part B is F equals mg. So the mass is, they gave us was 90 kilograms, times the g on this planet, which is 0.19, or this asteroid, which would be about 17 pounds. I'm sorry, 17 newtons. Because we're using kilograms, so our force is in newtons. Which is a lot less than what they would weigh on Earth, obviously. You can look at this as a proportion too. You can do 0.19 compared to 9.8 to find out the percentage. Basically, you'll find out that So it's about 2%, approximately 2% of gravity on this asteroid in comparison to Earth. That's not part of the problem, obviously, but your answers are here for part A and here for part B. Question. Next question, 74, says the moon's mass is 7.34 times 10 to the 22. And it gives us distance away from the Earth. It gives the Earth's mass, and it says calculate the gravitational force of attraction between the moon and the Earth. If you look at your formula sheet, that's this formula, universal law of gravity. Okay, so we're going to go ahead and enter this in, 6.67 times 10 to the negative 11 times the mass of the moon, for example, times the mass of the Earth. 5.97 times 10 to the 24, all divided by the distance between them squared. And they gave us that distance in meters, which is good. We just need to make sure we square it. So we should be able to do that in our calculator. Okay, it should give you approximately 2 times 10 to the 20th, and that's in newtons. Okay, so that's a huge force. Obviously, huge mass as well. That's part A. Part B says find the Earth's gravitational field at the moon. Okay, so part B wants the Earth's gravitational field. That formula's on our formula sheet. And it's right here. We just used it last time. Okay, so here's the Earth's gravitational field strength. It's the same as the formula for the acceleration due to gravity from the Earth at the moon, basically. So we're going to need to use the distance from the Earth to the moon right here for r. So 6.67 times 10 to the negative 11 times, we need the mass of the Earth, which was 5.97 times 10 to the 24, all divided by the distance between them, 3.8 times 10 to the 8th, and we need to square that. Okay, you solve that. Right there, you should get approximately 0.0028, and you can use meters per second squared, or it's actually the same thing as a Newton per meter. And a lot of times they'll use these units for gravitational field strength. So this is the units we would use for acceleration due to gravity. The acceleration due to gravity is the same thing as a gravitational field strength. They usually just use different units. This is a force per distance. I'm sorry, Newton per kilogram that we would use there. Which is the same thing as a meter per second squared. So this is basically how fast you would fall towards the Earth if you were on the moon, or if the moon wasn't there, then you were in free fall towards the Earth. And this would represent the gravitational field strength at the moon from the Earth. So there's about 0.0028 newtons of force for every kilogram of mass you have. All right, 81, on the surface of the moon, a 91-kilogram physics teacher weighs only 145.6 newtons. What is the value of the moon's gravitational field at its surface? So let's write down what we have. We have the mass of this person is 91 kilograms. We have the weight, so the force due to weight is 145.6 newtons. We want the gravitational field on its surface. Well, for this we could just do F equals ma and find that acceleration due to gravity, because that is the gravitational field strength, right? So that acceleration there would be the same as we would get if we did this for the mass of the moon. These should be the same value. Let's do it this way. We get 145.6 equals 91 times acceleration. Divide both sides by 91. We get acceleration equals 1.6. And you can do meters per second squared, but since we're talking about field strength, the same units would be newtons per kilogram. Okay? And that's exactly what we have here. This is newtons per kilogram. Right? So about 1.6 meters per second squared is the acceleration due to gravity of the moon. That makes the gravitational field strength 1.6 newtons for every kilogram of mass you have. Okay, so next problem is 84. It says if you weigh 637 newtons on Earth's surface, how much would you weigh on the planet Mars? So we want to know your weight on Mars. Okay. Mars has a mass of 6.42 times 10 to the 23 kilograms, and the radius is 3.4 times 10 to the 6 meters. Yeah, we can use universal gravity for this. This is F equals G times M1 times M2 over R squared. We know the mass of Mars. We know the distance that you are from the center of that mass, R. And we need to find your mass, but we can find that because we're given how much you weigh on Earth. So we can divide by 9.8 to get your mass. So we'll have all three of those variables, in which case we can solve for the... So F equals ma, so we know this equals m times a, and gravity on the Earth is 9.8, so we can divide both sides by 9.8 to get us the mass, which this person weighs 65 kilograms, or the mass, as it has a mass of 65 kilograms that's going in for their mass. Mass of Mars is 6.42, and then the distance between them is r. So we have 6.67 times 10 to the negative 11 for g, times 65 kilograms, times 6.42 times 10 to the 23rd kilograms, all divided by the distance, 3.4, times 10 to the 6 squared. Okay, if you do this in your calculator, you should get 235 newtons. So if you weighed 637 newtons on Earth, you'd weigh quite a bit less than that on Mars. Next is 86. It says find the value of g acceleration due to gravity in the following situations. Earth mass is tripled, its actual value, but the radius remains the same. So what we're going to do is write down the universal law of gravity. In the first one, the mass is tripled, its actual value, but the radius remains the same. If the mass is tripled, the Earth's mass, then we would multiply this by 3. And you can pull that out front if you want, that 3 out front, because multiplication is commutative, which means order doesn't matter. And you can see here's the original force of gravity, and if the mass is tripled, then the new force is 3 times as much. So we'd say 3 times g. So it'd basically be, the value of g would be 3g, or 3 times 9.8, which is about 29.4 meters per second squared. Okay, so part B, if the Earth's radius is tripled, then we're going to triple this value in here, but it's going to get squared. So I'm going to square that and pull that out as a 9 now, once I evaluate the square. And then I can multiply that 1/9 times the original. So here's the original force, and the new force is 1/9 of that. So I'd say 1/9 g, which is the same thing as 9.8 divided by 9, or about 1.08 meters per second squared. So if you were 3 times away from the center of the Earth as you are now, you'd only experience an acceleration of 1.08 meters per second squared. All right, for part C, if the mass and the radius were both doubled, well then the mass is doubled, but the radius is also doubled. You would need to square that and pull that out, so you would end up with the 2 can be pulled out, and the 2 squared is going to get pulled out as a 4, so you'd have this once you pulled those numbers out. And here is the original force right there due to gravity, and the next one's going to be 2/4 of that, which is 1/2 of that. 1/2 g is the answer, or approximately 4.9 meters per second, if the mass and the radius are both doubled. Okay, so last one, what would be the field strength of the Earth at a point 80 kilogram would experience 25% reduction in weight. 25% reduction in weight must mean 25% of the gravitational field strength in order for this direct relationship to remain true. So it'd be 1/4 of gravity of 9.8, which gives you about 2.45 meters per second squared. They wanted that gravitational field strength to actually be we'll use Newton per kilogram there instead of for the units. Same units, different way to represent them.